welcome back. We're covering section 7.8, improper integrals. So here we're going to say that we look at the integral a to b of f of x dx. F of x was defined on a finite closed interval from a to b. We want to extend this idea. So we're going to say uh, the integration of a to b of f of x dx to say, in one case, the interval is infinite. So we can go from a to infinity, or infinity to b, or even infinity to infinity. And then in case 2, f has an infinite discontinuity. In other words, there's a vertical asymptote there, right? Something's happening there, so it's going to go into infinity at that point. It's discontinuous. So here's type 1 of the infinite intervals. We're going to say we're going to look at the interval from 1 through infinity of 1 over x squared dx. And that's the same as saying the limit as t approaches infinity of 1 to t of 1 over x squared. Right. Which could turn out to be 1. Let's look at this. So if we look at we're going to say the limit as t approaches infinity of 1 over t x to the minus 2 dx, we end up saying it's the limit as t approaches infinity of negative 1 over x to the 1 to the t. And we evaluate this integral 1 over t. Well, that's going to go to 0. Subtract this, which is just 1. So we can say that this integral approaches 1. The definition of an improper integral of type 1 says if the integration of a to t of f of x dx exists for every number t greater than a, then I could say that instead of going from a to infinity dx, f of x dx, I can look at the limit as t approaches infinity of a through t of f of x dx, provided the limit exists as a finite number. So now I have a way to evaluate, because I can't look at infinity, but I can look at what's happening as I approach infinity. And this is an important concept for when we get to chapter 11. Now, in here, we're going from a to infinity. Now we're going to say from minus infinity to b. So it says if t to b of f of x dx exists for every t less than or equal to b, then we can look at the integration of minus infinity to b of f of x dx is equal to the limit as t approaches the opposite of infinity or minus infinity, t to b of f of x dx, provided this limit exists and has a finite number. The improper integrals, so now we're going to say the improper integrals of a through infinity of f of x dx and the improper integral of negative infinity to b of f of x dx are called convergent if the corresponding limits exist. So what we're saying is if I could find a finite number, then we could say that these are convergent. And again, this is a huge concept for chapter 11. And then they're divergent if the limit does not exist, so if it goes to infinity. Now here's where it really gets interesting. It says if both the integration of a to infinity of f of x dx and minus infinity to the integration of minus infinity to a of f of x dx are convergent, then we define the integration of negative infinity to infinity of f of x dx equal minus infinity to a of f of x dx, picking up at a, going to infinity of f of x dx, where any real number a can be used. In other words, the sum of the integrations is equal to the integration of the sums. So I can't evaluate this here from negative infinity to infinity, but I can evaluate from negative infinity to a, and I can take the limit of this. And I can do the limit of this one, picking up at that same point, going to infinity. Sum them up, and then I could get a result. So let's get started. I'm going to look at the limit as a. They use t, I use a, it doesn't matter what I call it, of a to negative 1 of e to the minus 2t dt. So now I'm going to say let u equal minus 2t. du is equal to minus 2 dt, or minus 1 half du is equal to dt. So I have my substitutions, right? I can then say I'm looking at the limit as a approaches negative infinity of a minus 1 half a to negative 1 e to the u du. So now I can integrate that, the limit, and I expect you to write all this information down for me. Instead of e to the u, I'm just going to write it back with my t's from a to negative 1. And then I'm going to say it's the limit. I'm going to do my substitution. E to the minus 2 times negative 1 minus e to the minus 2 times a. Well, a is going to negative infinity, so I have a negative 2 times that. That's going to go to a positive infinity, right? This whole thing here is going to turn out to be a positive infinity, so this whole thing is going to infinity. It doesn't matter what this part's going to. I have, let's say, e to the 2 minus infinity. Well, that whole thing, even if I take a little bit of it or add a little bit to it, it's still going to infinity. We're going to say that this diverges. So the limit of this thing goes to something, goes to infinity, and diverges. Therefore diverges. Now we're going to look at another one. So before we went from negative infinity to negative 1, now we're going to go from 0. So we're starting someplace and going to infinity. I'm going to do the same thing I just did before. Limit as t approaches positive infinity from 0 to t of 1 over 1 plus x squared dx. So we should recognize the integration of 1 over 1 plus x squared dx. That should give me arctan of x. So I get the limit as t approaches positive infinity of arctan of x from 0 to t. Now it's helpful if we kind of know what arctan looks like. So I'm going to do, just remind us real quick, take a couple seconds. That's pi over 2 minus pi over 2. And then draw a quick function. So it looks something like this. It's two horizontal asymptotes at pi over 2 and minus pi over 2. So I'm going to look at this as the limit as t approaches positive infinity of the arctan of t minus the arctan of 0. Well, the arctan of 0, that's 0 because it's right here. And this, what we could say is looking at this thing, as it's getting larger and larger, it's getting closer and closer to that pi over 2, so it's going to approach pi over 2. So this part is pi over 2. I have a pi over 2 minus 0, which is just pi over 2, and there's my answer, pi over 2. So we would say this converges, because it converges to a finite number, or a fixed number. So now in this example, we're still looking at the arctan, but instead of going from 0 to infinity, we're going to break this apart, because we said back here a few slides, oops, went too far, that I could break it apart. And I could break it apart anywhere. And I'm going to choose to break it up in a specific spot. So I'm going to say the limit as a approaches minus infinity of a to, I'm going to go to 0 because it's a nice easy spot to look at. 1 plus x squared dx plus the limit as b approaches positive infinity of 0, because I got to pick up where I left off, to b of 1 over 1 plus x squared dx. So now I've broken it apart. Starting from a to 0 and from 0 to b. And now I'm going to look at the limit as a approaches minus infinity of of the arctan of x from a to 0 plus the limit as b approaches infinity of the arctan of x from 0 to b. And as we saw in the last slide, we know what arctan looks like. This is going to be the limit as a approaches minus infinity of the arctan of 0 minus the arctan of a plus the limit as b approaches positive infinity of the arctan of b minus the arctan of 0. Well, that's a 0. That's a 0. We'll just change colors here. It's getting messy here. That's going to minus pi over 2 because it's going to minus infinity. And that's going to pi over 2. It's going to positive. So I have a minus pi over 2 plus a pi over 2. I add them together. Minus and minus is plus. The answer is pi. Converges. So these are simple, but there's a lot of stuff you need to write. I want to see that you're telling me you're taking the limit and write it to a. Don't go to infinity. You can't evaluate it at infinity, but we can evaluate the limits. I will take off on the test. It's important. All right, it's being sloppy if we don't do it that way. So now we're going to look at this problem, and again I can break it apart. So what I'm going to do is first I'm going to do a u substitution. I'm going to say, let u equal minus x squared. Du is equal to minus 2x dx, or minus 1 half du is equal to x dx. And that's good because here's my x and there's my dx. So I have the integration negative infinity through infinity of an e to the u du, and I have a minus 1 half out front. This is another one where I can break it apart, so I will break it apart. The limit as a approaches negative infinity, and I have a 1 half out here, negative 1 half, right, of a to 0 of e to the u du plus the limit as b approaches infinity of 0 to b e to the u du, close the parentheses. I can evaluate this. I can integrate it now. It's the limit as a approaches minus infinity of e to the u from a to 0 plus the limit as b approaches infinity of e to the u from 0 to b. But instead of u, I can make it a minus x squared, so I'm going to change that right here. And now we're going to evaluate this. I have a minus 1 half times the limit as a approaches negative infinity of e. I'm just going to put the 0 minus e to the minus a squared plus the limit as b approaches infinity of e to the minus b squared minus e to the 0. So now I'm going to look at these and change the ink colors again. So e to the minus 0, well, that goes to 1. That's a minus 0. It doesn't matter. That's going to go to 1. And now e to the minus a squared. Well, a is going to negative infinity. I'm squaring it, and when I square something, it's going to be positive. So I have a minus infinity. So this is really a minus infinity. So that means this whole thing is going to 0. And the same thing's going to happen here. This whole thing is going to go to 0 because I have e to the minus infinity, or 1 over e to the infinity, which is going to go to 0. So now I have a minus 1 half times 1 minus 0 plus 0 minus 1. So I end up with a minus 1 half times 0, or just 0. and we'd say it's convergent again. All right, let's look at the next slide. So we just did something similar to that. All right, and we're actually going to skip this one. It's going to go to 0 to 1. I think we've seen enough of these examples. We're going to skip this one and get to the next slide and start talking about the p-series. So hold on for a second. Actually, I thought about this for a second, and I'm only 15 minutes into this, so I think I have enough time to actually do this problem real quick. So let's just look at it real quick, only because it's a different style of problem. So I'm going to look at the limit as a approaches infinity of a to 0 of f of x e to the x dx. This is a parts problem. All right, so I'm going to let u equal x, du equals dx, dv is equal to e to the x dx, so v has to be e to the x. So I'm going to look at the limit as a approaches infinity. So we haven't done a whole lot of parts problems, so it's probably a good idea to practice u times v, x e to the x minus the integration of v du, e to the x dx. This is an easy integration. And by the way, this is from a to 0. X e to the x minus e to the x. We're going to evaluate this real quick. This is going from a to 0. So I put 0 and I got 0 e to the 0 minus e to the 0 minus a e to the a minus e to the a. All right, well, this is 0. That's going to go to 1, so I have a 1 here. That's going to 0. All right. And then, hold on for a sec. Yeah, because we're going to minus infinity. So that goes to 0. And then the problem is I have a minus infinity times e to the minus infinity, or in minus infinity times 0. So the thing is, I need to figure out what's happening here. So far, it looks like it's converging. We know it's going to converge to 1. We just have to prove it real quick. So let's work on that part. I'm going to rewrite this as x over 1 over e to the minus 1 over e to the x, or I can say x over e to the minus x. And when I do that, I end up with infinity over infinity. Because remember, the limit as a approaches negative infinity. So I have e to the minus infinity, which is just e to the infinity. All right. So now that I have that, I can apply L'Hopital's. Don't forget to write the LH. And I'm going to look at the limit as a approaches minus infinity. The derivative of x1, derivative of e to the minus x is minus e to the minus x. Now I have 1 over infinity, so this whole thing is going to go to 0. That means this part here goes to 0 by what we just showed down here. All that's left is this minus 1 here. So the answer is minus 1. I know I went over that quickly, but I wanted to show you this one because it did this in using integration by parts, and I think it's important to see that in practice. Integration by parts comes up, and it also forces us to look at a L'Hopital's, which is what you needed for your first test, or test 2, I'm sorry. I meant the first test for chapter 7 material. So, by definition, we say that the integration from 1 through infinity of 1 over x to the p dx is convergent if p is greater than 1 and divergent. This is called a p-series. We're going to learn about this plenty in chapter 11. I'm going to show you in chapter 11 why it converges, but right now I'm not concerned about that. Just have to accept the fact that it does converge. So now I want to look at this, and this is a big mistake. Because we're going to say, look at this. I'm going to integrate from 0 to 3 of d of x all over x minus 1. And if I integrate without looking at what's going on, I get the integration. I end up with the natural log of the absolute value of x minus 1. And I end up with this. But the problem is, what happens at x equals 1? It's in the middle of my interval. That's not good. You cannot do this. We have to break it apart. Remember, we were breaking apart the other ones. When we're going to infinity, we broke it apart. Well, we have to break it apart where there's a discontinuity. So it says this is the definition of an improper integral of type 2. Because if f is continuous on the interval a through b and is discontinuous at b, then we have this. We worked on this part, right? So now this is a closed interval. Before we had the open interval. This limit exists. It's a finite number. Then we say, again, if it's continuous on the interval, so it's not quite what we were looking at yet, then it does the same thing. I could say from a to b, except for at a, then I use the limit of this. But what happens when it's discontinuous in the middle? We're going to see a problem like that. We're going to actually address the problem we had just saw a couple of slides ago, the d of x minus 1, d of x over 1. So in here, it's discontinuous at the start. So we say the limit as a approaches 2. And where am I approaching to? From the right, right? Because looking at it, here's 2, here's 5. I want to approach from this right-hand side of that. So we're going to say 2 to the right of a to 5 of 1 over x minus 2 square root d of x. Now, instead of writing it this way, it'd probably be easier to write it in exponential form. And then I could probably clearly see that I could do a u substitution. Let u equal x minus 2. du is equal to dx. So now I'm going to look at the limit as a approaches 2 from the right again. A to b. Instead of x minus 2, it's u to the minus 1 half du. Well, this is a lot easier to integrate now. I have the limit as a approaches 2 from the right of u to the 1 half. There's a 2 here. Sorry, I gotta write this in English now. 1 half u to the 1 half, because the negative 1 half plus 1 is 1 half, and I'm evaluating from a to 5. I don't know why my 5 looks like a b there. All right, so now we're going to look at the limit as a approaches 2 from the right of 1 half. Instead of u, it was x minus 2, so x minus 2 to the 1 half, a to 5. And now let's evaluate this. Limit is a approaches 2 to the right, 1 half times 5 minus 2 to the 1 half minus 2 minus 2 from the 1 half. Now remember, we're approaching from the right, so it's a little larger than that 2 that I'm subtracting, right? This 2 here, right, that's for my a, is slightly larger than this. So it's always going to be positive. And I can take the square root of any positive number. It's going to approach 0, so this whole thing's going to go to 0. So it's 1 half times 5 to the half, or 1 half times square root of 5. Oop, 3. I can do math. Don't mind me. Last time I checked, 5 minus 2 is 3. And 1 half the square root of 3. 2. So, where'd I get 1? Wow, am I making some really dumb mistakes, right? This is 2 here. Actually, let me put it in a different color because I made a mistake and I want to make sure we all see it. This is a 2. I had wrote a 1 half. This is a 2. This is 2. This is a 2 here. This is a 2 here. And this is a 2 here. I apologize for that. Thankfully, I looked down on my notes and I saw that I had wrote something differently. That converges. I apologize. Sometimes I get ahead of myself. I'm thinking about something else and I make my mistakes too. So again, that was a 2 because this, when I integrate this part, it has to go back to u to the minus 1 half. And that's the only way I can do is to have a 2 in front. All right, so now we're going to look at this problem. But before I do anything, I could rewrite this 3 to 0. 1 over x to the times x to the 1/2, or dx. 0 to 3. I can add my exponents, and that's a 3/2. So I can look at this as 0 to 3 to x to the minus 3/2 if I want dx. So at 0, right? At 0, there's a problem. It's not continuous at 0. It's an open interval, not a closed interval. So we're going to say the limit as a approaches 0. And again, I'm going to come from the right of a to 3 of x to the minus 3/2 dx. So let's evaluate this, the integration. A to 0 from the right, x to the minus 1/2, 2, negative. All right. And that's a to 3. So I have the limit as a approaches 0 from the right. I'm going to put a minus 2 up front. 1 over 3, the square root of 3, minus 1 over square root of a. Well, as a gets larger, or as a gets smaller and smaller and smaller, the whole thing is going to approach infinity, correct? If that's the case, it doesn't matter that the right-hand side approached a specific number. I can't add them together, and it diverges. So this is a divergent problem. But let's go back to what we talked about here. Where'd it go? P series. This is 1 over x to the p from 1 through infinity. Let's see, what are we doing? Are we doing 1 through infinity? Oh, we're going to a finite. Sorry, I thought we were going to infinity, so I can't use the idea of a p series. So now I have x minus 1. That's the problem that we started off with, that we showed doing the limits as 1. We took the natural log. We can't do that. But now we know it's discontinuous. So at x equals 1, so I have to take the limit as a approaches 1 from the left, because I'm going to go from here's 0, here's 1, here's 3. First I'm going to do this part, and then I'm going to look at this part. So the first part I'm worried about is going to go from the left, and that's from 0 to 1 from the left of 1 over x minus 1 dx, plus the limit as b approaches 1 from the right this time, because I'm still approaching the same number, it's just I'm approaching from another side, b to 3 of 1 over x minus 1 dx. So this is just a natural log still, so it's the limit of a approaches 1 from the left of the natural log of the absolute value of x minus 1 from 0 to 1 to the 1 to the a. I should have put a negative 1. That's plus the limit as b approaches 1 from the right of the natural log of the absolute value of x minus 1 from b to 3. All right. Well, if we look at this, we're going to look at the limit as a approaches 1 from the left of the natural log of a minus 1, subtract the limit as, oops, not the limit, but the natural log of 0 minus 1. I'm going to stop here for a second because I want to talk about a couple things. We're taking the absolute value. So it doesn't matter that's a negative 1 in there. That whole thing is going to approach positive 1. It's the natural log of 1, so this thing is 0. What's interesting is here, I have the natural log of 1 minus 1. That's going to 0. The natural log of 0 is going to approach negative infinity. And because of that, I do not need to worry about this half of the problem. I don't care what's happening on that half. I'm divergent. I'm divergent because of this. Oops. I'm divergent because of this right here. Right. That part there makes the entire thing divergent. All right. So I don't have to evaluate the rest of it. If part of it's divergent, the entire thing's divergent. So now it says the improper integral a to b of fx dx is called convergent if the corresponding limits exist, and divergent if the limits do not or does not exist. So remember, we're looking to see, I could tell it's convergent if the limit exists, and I could tell you it's divergent if the limits don't exist. It says if f has a discontinuity at c, where a is less than or c is less than b, and both a through c of f of x dx and the integral of c to b of f of x dx are convergent, then we define that. And this is, we did this when we were doing the infinities, and it's the same thing because I could sum them up, which means I could break them apart. If each part converges, then the whole thing converges. If one or more parts diverge, then it's divergent. So now we're going to do what's called the comparison test. It's an important test, and I want you to see how this works. We're going to use the comparison test a lot when we get into chapter 11. It's one of the things that allows us to get out of some of the issues of having to find convergence. So a comparison test for improper integrals says, suppose that f and g are continuous functions with f of x being greater than g of x, and they're all positive. They're greater than or equal to 0 for all x greater than or equal to a. In a here it says, if f of x dx is convergent, then the integration from a to infinity of g of x dx is convergent. Well, that makes sense, because if I have two functions, this is my first function, which I don't know how to define, and this is my second function, right? If that larger function here is convergent, this function down here must be convergent because it's below it. If this function in red is smaller than the function in blue, and the blue is convergent, red has a ceiling. It can't get bigger than the blue one, so it will converge. But now it says if g of x dx is divergent, then f of x is divergent. So again, if the smaller one is divergent, so this is my smaller one, I don't know anything about f of x. Well, the problem is this one's divergent. I'm always going to be larger than the one that's diverging in red. So again, I have a bottom, and I have to, that red function is going to go through me if I converge, and I can't converge then. I have to diverge because the red one is smaller than me all the time. I can't have it ever be larger than me. So it will diverge. So we're going to use this concept to do things. And here are some things that will help us solve some of our problems. It says, look, if f of x is greater than 1, then I know that x cubed has to be greater than x squared, which has to be greater than x. And we're going to use this concept to build our arguments. Some other things I can use is I know that sine of x is always greater than or equal to -1, and it's always less than or equal to 1. And same thing with cosine. What's even more interesting is that sine squared is always less than or equal to 1, and cosine squared is always less than or equal to 1. So I can use that to help me. And then e to u is greater than 0 for all powers of 0, of u. Because e to u will, it's, right, e to u looks like this. So it never gets negative. The value's never, it approaches 0 when it goes to the left. So let's look at this problem. I don't know how to integrate e to the minus x squared, so I can't tell what's going on here. But what I do know is that x squared is greater than x, which is greater than 0. And then if I take the reciprocal of all this, that's true. And I could do that by, whoops, sorry, I went too far. I'm thinking about something else. If I take the opposite, because this has the opposite, if I multiply it through by the opposite, then we switch the inequality. So that's a true statement now. And if this is true, therefore, e to the minus x squared has to be smaller than e to the minus x. And if that's true, and this is how I want you to build your arguments, then 1 through infinity of e to the minus x squared dx has to be smaller than the integration of 1 through infinity of e to the minus x dx. Why do I care about that? Because I am not good. I don't know how to integrate this, but I sure do know how to integrate this. And if what's in blue, e to the minus x, is convergent, then e to the minus x squared has to be convergent because it's smaller, and it will always be smaller. So I'm going to look at the limit. As a approaches infinity, of 1 through a of e to the minus x dx. When I integrate that, I get the limit as a approaches infinity of e to the minus x with a negative in front of it, 1 through a. I'm going to evaluate now. E to the minus a, subtract negative e to the minus 1. All right. So let's look at this. As a gets larger and larger, goes to infinity, I really have a minus infinity. Well, that means I have a negative 1 over e to the infinity. Well, that whole thing's going to go to 0. Plus e to the minus 1. Well, e to the minus 1 is just 1 over e. I'm convergent. All right, so we'd say by the comparison test, 1 through infinity of e to the minus x squared dx converges. And I can get away with not saying that the green one's smaller than the blue one, again, because I told you at the beginning that that was true. I've established my argument. Everything here is everything I would need to prove that that's a convergent function. So now, I want to show that this is divergent. So this is an interesting one to build up. I could say e to the minus x is greater than 0, because that's what we said earlier. E to the u is always greater than or equal to 0. I can add 1 to both sides and not change the inequality. Now I could take I'm not going to take the reciprocal. I could divide everything. I'm going to divide by x. And when I divide by x, x is going from 1 through infinity, so x is positive. It doesn't change my inequality. And if this is true, then I know that from 1 through infinity of 1 plus e to the minus x over x dx has to be greater than 1 through infinity of 1 over x dx. That's great, because remember we did the p series earlier? This is 1 over x. It's a p series. P is equal to 1 because x is the first power. P equals 1. And that's less than or equal to 1, and it's divergent. And if that's divergent and it's smaller, right? If this series is smaller and it's divergent, then the larger series must be divergent. So then, because therefore, by comparison tests, 1 through infinity of 1 plus e to the minus x over x dx diverges. I don't know what it goes to. I don't know how it diverges. I don't care that it diverges. I just know it diverges because of that p series, and I'm larger than the divergent series. So now we're going to look at this, and we're going to say, well, how can I do that? Sine squared. Again, I don't know how to do that. I have 1 plus x squared. Well, that kind of reminds me of an arctan. I have a sine squared x. I don't know how to handle. But earlier I said sine squared x is less than or equal to 1. So I'm going to say, oh, that's great. So let's say sine squared x, it's always less than or equal to 1. And I can divide both sides by a positive value and not change my inequality. So I get sine squared x divided by 1 plus x squared. That has to be less than or equal to 1 over 1 plus x squared. And that's great, because then I can say that the integration of 1 through infinity of sine squared x with 1 plus x squared is dx is less than or equal to 1 through infinity of 1 over 1 plus x squared dx. And now I've created something I know how to handle. That there is the arctan. And if I'm smaller than that series and that integration, and that integration converges, then I must converge, or sine squared x plus over 1 plus x squared has to converge. I don't know what it converges to, but I'll know that it converges. That's all I'm asking for. So I say the limit as a approaches infinity, 1 over 1 to a of 1 over 1 plus x squared dx. I want to prove that that converges, so I'm going to say the limit as a approaches infinity. Again, that's arctan of x, and I'm evaluating from 1 through a. Whoops, went a little too far. That's the limit as a approaches infinity of the arctan of a, subtract the arctan of 1. Well, the arctan of a, that's infinity, so this is going to go approach pi over 2. And what I want to subtract from it, well, when does tangent equal 1? Well, that happens, positive 1. We're looking arctan, so it's going to be from minus pi over 2 to pi over 2. That happens at pi over 4. Remember, we have to remember the where the interval is for arctan. It's from minus pi over 2 to pi over 2. So I have that, I sum them together, and I get a pi over 4. That converges. Therefore, by the comparison test, 1 through infinity of sine squared x over 1 plus x squared dx converges. And again, I don't know what it converges to, and I really don't care what it converges to. I just know it does converge. And that's the whole idea that we're going to use in chapter 11. Sometimes we don't care that they converge. I just want to know that they converge or diverge. Here's another problem. So how am I going to build this one? Well, some things I know. I know that e to the x greater than 0 for all x, right, that are elements of reals. And then I can add to both sides. X squared plus e to the x has to be greater than x squared, because x squared is a positive term, and I'm allowed to do that. Then if I take the reciprocal of something, I'd flip the sign. And here's a quick note. Example, 1/3 is smaller than 1/2, correct? But if I took the reciprocals, 3 is greater than 2. So it's just a simple thing. When I take the reciprocals, the inequality changes direction. So now that we've established that this is true, then we can say that 1 through infinity of 1 over x squared plus e to the x dx has to be smaller than 1 through infinity of 1 over x squared dx. Why do I care? That's a p-series. So I know how to handle that one because I was given that information. So we say p-series. P is equal to 2, which is greater than or equal to 1. Therefore converges. And if that converges, then the smaller one has to converge by the comparison test. Therefore, by the comparison test, the integration from 1 through infinity of 1 over x squared plus e to the x dx converges. And I'm allowed to do that because here's where I've established, right? That's where I established that this function is smaller than that function. And if the larger function converges, the smaller function must converge. If the smaller function diverges, then the larger function must diverge. So here's another one. We're almost done. I think we have one more. This might be the last one. I'm not sure. Yep, this is the last one. So how do I build this one? Well, I could say the cosine of x is less than 1, less than or equal to 1, for sure. Right? It's equal to 1, but it's less than or equal to 1. I can multiply both sides by x. And I know it's greater than or equal to -1, but I only care about one side at this point because I want to see if that works. I'm going to multiply both sides by x, and I can do that because it's positive, and it won't change my inequality. So that's true. All right, I'm going to write myself a note. x is greater than or equals 0. That's why I was able to get away with not changing the inequality. Again, the whole idea of the reciprocals help me out sometimes, so I'm going to try that because it gets me to look like the problem I originally had. 1 over x. And that's interesting because 1 over x is a p-series. So I know how to take care of that one. I don't have to do anything special. So I'm looking at 0 to pi over 2. I'm going to establish my argument that 1 over x cosine of x dx is larger than or equal to 0 to pi over 2, 1 over x dx. Then I'm going to say, well, that's nice because that is a p-series. P is equal to 1, which is less than or equal to 1, therefore diverges. Yes, you need to know about the p-series. You're going to memorize it. It's not on that list that I give you. I'm almost done. I can say by the comparison test, 0 through pi over 2. Let's write this a little nicer. Of 1 over x cosine x dx diverges. I've already established earlier which one was bigger and which one is smaller. I'm just going to use that fact, right? Because again, my larger function compared to my smaller function. If my smaller function diverges, then my larger function must diverge because of how they are set up. Okay, well, that's the end of this video. It's 46 minutes long. Hopefully you enjoyed it, and I'll see you in the next class.